Do you see the slides? Do you see the presentation?
Yes.
Okay, great. So we'll get started. Okay, so we continue to talk about model evaluations. Mostly we're talking about classifications, and also most of these concepts will apply only to binary classification problems where you have a positive and negative label, and the machine learning problem is the classification problem. Otherwise, a lot of these will not apply. But because binary classification problem is the most prevalent or common tasks in machine learning applications, that's why we focus a lot on that. It's actually, it have a lot of concepts to evaluate model performances, and it's closely connected to practice. So again, these are the concepts that's relevant. The fourth homework has a few questions, a couple, I think, conceptual questions, but a few more hands-on questions to calculate specific concepts by using codes. You use both like by hand from scratch, which means you use the appropriate variable that's defined or that's provided to you by the question, and you basically hand type the formula, like plus and division and parentheses, to calculate the value based on the formula. And also you use packages, appropriate functions from those packages to calculate the same thing, and hopefully the two will match. So that's a concept behind those questions. And model evaluation is not, especially for binary classifications, it's not as complicated. So that's how we don't have to spend too much time. A lot of it is intuitive. When we talk about the cases, about how to judge decision analysis, and as well as how to judge the performance of the model, most of them will come as intuitive. But there is certain parts that will require more effort, to the extent that you probably need to memorize something. I'll talk about that when we get there. Oh, okay, so let's refresh your memory about several terms that I talked about, and we'll probably have some bonus questions. This time we'll open it to virtual as well. We'll have a little bit fun mix and fun. So what is Fn? False negative, which is an error whenever, and before that, in terms of binary classifications, there are two outcomes that we define, or two labels. Say outcome, we say label, we say event. So these are the same thing. We have positive and negative. Can you explain what positive event is? And you can make an example to explain that. And we'll open discussion to virtual as well. If you volunteer, let me know, and just go ahead and say you want to answer a question. Identify yourself, and then we'll go from there. So how do we define a positive outcome or positive event? How do you understand that? or if you can make an example, will be better. Anybody?
Positive is simply yes. Example, testing for COVID-19. Having COVID-19.
That's great. So Alex framed the event as diagnosis in the case of COVID. I think that would be the most intuitive or timely example, which is correct, right? Positive doesn't mean good. Essentially, obviously having COVID is not good, but it's a yes event. Okay, and so the opposite is negative. Negative doesn't mean bad, but in a medical term, it's immediately clear. Negative is good, actually, right? Positive is not. At least positive requires more attention. Negative can be dismissed. So that's great. In businesses, can we have more examples?
Can I add the example, Professor?
Yeah, go ahead, Lily.
Sure. Yeah, I wanted to mention, for example, marketing campaign. So we can define some different attributes can affect on the customer that they want to purchase the particular product, and the target it's going to be yes or one when they purchase it. For example, when we approach them, or when we do advertising in front of the customer, or when we do some promotion on all of these variables. And then when they purchase this product after advertising and all these attributes, it's going to be one, and it's going to be a positive. And if they don't purchase it, we say it's 0 or no. And yes, and if it is true positive, that means our prediction and our classification for this target variable was true and it was positive, and it's false positive. That means the actual result is positive and the customer purchased that product, but we estimated in a wrong way.
Great, excellent. So in terms of customer decisions, essentially, a positive event is actually desirable. And in both cases, I would say, as well as in most cases, positive events tend to be the minority, tend to be less likely. So in terms of COVID, we know that the infection rate of COVID is probably 50 per 10,000, something like that in population level. And the conditional on COVID diagnosis. So given a positive test, what's the death rate? So death would be another target and target variable, and death would be the positive event, right? The death rate is essentially 2% or below that. So that's minority. All of these can be subject to be predicted. In terms of business, customer purchase decision is also, tend to be a minority event where, almost no business can guarantee a customer purchase rate of over 50%. It's more likely below. That's why it's harder to predict, or it's harder to achieve, just given the varieties. But of course, there are certain exceptions. When it comes to Windows operation systems, you can almost guarantee, because the market share is huge, is so significant for Microsoft. It's just, so they deal with different questions. They don't really care about whether or not a given customer will get Windows operating system, but rather how to deal with the problems, how to continue their, I guess, acceptance of the operating system. They really don't want them to switch over to Mac. So that's really the problem there. But yeah, in most cases, a business or not, the positive event is less likely than the negative event. Okay, so when we discuss the prediction decision or classification decision, which is a recommendation that's derived from machine learning models, then we have true or false. So can you explain what is true and what is false, regardless of the positive or negative? Or you can mix and match and use that to make an example. So what does true mean? What does false mean? Anyone?
Can I explain it?
Yeah, go ahead.
So true positive, that means we predict the target variable in the correct way. So for example, the actual result is going to be positive, and we predicted exactly positive. But when the answer is true negative, it's false negative. That means the actual was negative, and we predict the target variable in a wrong way. And true negative, it's going to be we predicted the target as negative, and it was negative in actual. And false negative, that means we guess negative, which it was the target variable was true, and we predicted in a wrong way.
Mm-hmm. Yeah. So true and false is a judgment on the prediction decision of the algorithm as compared to and based on the ground truth, basically. Right. So there can be two truths and two false. And in case of false predictions, the actual ground truth is the opposite to the predicted label. It's it's a little bit of convolutional, if you will. So, but to be able to make a quick, judgment based on the label requires some little getting used to, right? So, so that brings out the confusion matrix, which is basically a 2x2 table with 4 cells, and any prediction algorithm will turn out to have 4 of these statistics: true positive, true negative, and false positive, false negative, and they will fill in the numbers. So, and let's establish some kind of habit here and rule. For me, I think most people, most domain experts prefer that. Rows will denote ground truth. We say outcomes. So those are the rows. And 1 will typically be the row above, 0 will be the row below. So positive outcome will be the first row, negative outcome will be the next row. And the columns will denote the predictions or predicted labels or classifications, whichever you want to call it. And critical is where you write 0 or 1. That will make a huge difference in terms of how you read the numbers in hold on, what's happening? In terms of how you calculate Do we have here? Let's see. I don't seem to be able to change it, but my habit is to always have the label 1 positive to come first. So that way you identify the diagonal line, which is the 1, 1 or 0, 0, as to be this line that occupy these two cells. Those are the true labels. Those are the true cells. The off diagonal would be the false, right? So establish that habit and consistently use that will be easier over time. When I make when I make homework questions, exam questions, or in class questions, I will always stick to that format. When you look at materials elsewhere, the first thing you want to make sure when you attempt to read the confusion matrix in papers, in textbooks, is to pay attention to the structure of that, the layout of the confusion matrix first. Make sure you know which is which before you go ahead and read it. Sometimes it will do 0 and 1, 0 on the left, 1 on the right, and 0 on the top, 1 on the bottom, which makes sense because 0 comes first. And in that case, the way you read the confusion matrix is entirely flipped. It's a kind of a mirror flip. So that, and the two, if you add these 4 together, these 4 statistics, we say, they are mutually exclusive, right? They don't have any overlap. True positive and false negative, they are mutually exclusive. And same with the other labels. So any 2 of these or any pair of these are mutually exclusive. If you add them all together, that's going to be the size of the entire training data set or testing data set. That's the entire data set. If you add true positive and false negative together, that would be the total number of what? So to answer that question more comfortably, put that into the grid first. That would be helpful. True positive, pretty obvious. It's in this cell. Where is false negative? False negative, because it's false, it's off diagonal. And because it's false negative, it's a negative prediction. So it's going to be the second column. So false negative would be the second column, the first grid. So if you add them together, it's going to be the first row of this table, of this confusion matrix. And what is the total of the first row? If you know the answer, just go ahead. Huh?
All the actual positives.
Right, the positive cases. So that, that helps better, at least to get started, be familiar with that. And if you add the total of these 2, true negative and false positive, by logic you can immediately tell it's the total of negative cases. But how can you quickly derive, or how can you quickly answer the question without knowing the other side? If you jump into any question, can you form a correct judgment immediately? That takes some used to. Using this confusion matrix helps at least be more familiar. Another way or another question, if you add true positive and false positive together, what would it be?
True positive?
Huh? Say it again?
A positive? A positive or true positive?
I still cannot hear very clearly. You said positive. What does that mean? Anyway, so if you add true positive and false negative together, what is that? What is that total? Or what is the part of that confusion matrix?
Positive outcome.
Positive outcome, which means the first row.
Yes.
Think about it. Does it make sense? So true positive is this one, true positive. False positive, what is it? It's false. It's off.
First column.
False, no, true positive and false negative is the first row.
Okay. So that was the previous question. The question I'm asking now is, that's fine. True positive and false positive.
Okay.
What is it?
And false positive.
It's the first column. It's
the first column.
It's like true
positive.
prediction.
So
or correct prediction.
So it's going to be the total number of positive predictions that you make. Yeah. Because all the positive predictions, whether or not it's true or false, would be in the first column. Make sense? Because it cannot be the second column. The second column is all about negative predictions. Some are true, some are false. Yeah. Make sense? All right. Now, given these, we can take it further. So how do I clean it? I don't know. Oh, here. So, yeah, should have kept it. So when you have true positive, then you can have true positive rate. Since it's true positive rate, it is describing some kind of a, I guess, goodness of performance, because it's true positive, right? So it's a rate that describes how well the model is doing. That means the higher the better. True positive rate, if it's 100%, it's great. It's 30%, it's not good. You know. So what is true positive rate? If you flip to the next slides, the following slides, you will find out the answer. Here, I'm just trying to prompt you to think about it without looking at the answer. True positive rate is true positive rate. Obviously, you would have true positive on the numerator, but the question is, what's the denominator? And you would still include the true positive in the denominator, but what is the other side?
False negative.
False positive. We need to divide them by all the positives. So true positive plus false positive.
Hey, we have a competing answer. I think Reynolds said false negative. Lily said false positive. I'm not, you know, there's no winner or loser, by the way, but we just want to use this to clarify. Huh?
I think we should get to vote.
let's do that.
The vote gets the
Well, it's hard for virtual to vote, but yeah. Anyway.
Sorry, can I correct myself? So all the positive, it's going to be true positive plus false negative. Then the answer is going to be the total of all positive.
Right. So, correct. And nice work, and as well as nice work, Reno. So the key here is to be clear about whether or not it's predictions or whether or not it's outcomes. When you say all the positive, what do you mean? Do you mean all the positive predictions, or do you mean all the positive outcomes? If it's all the positive outcomes, it's going to be true positive, of course, but the other side, the other part of the positive outcome is actually false negative. That's kind of, that's why it's convolutional. So be clear on that. Whenever we say rate, we have 4 different kind of rates here. A true positive rate, true negative rate. We have false positive rate and false negative rate. We have 4 kinds of rate, which makes sense because there are 4 cells here, right? So you can make 4 different kinds. So I'm not going to iterate through all of these, but you get the idea. We also have a more general, these are more specific to a particular label or outcome, but a more general model evaluation matrix would be, or 2 more general matrix measures would be accuracy and error, and they are to the opposite of each other. When you have an accuracy, the error is 1 minus the accuracy, so they complement each other. And for accuracy, we have both the true labels or true cells, which is on the diagonal line, and you have all on the denominator, everything included on the denominator. So that's the percent of true predictions, regardless of positive or negative. And the error, of course, would be the opposite. You can do 1 minus, but to be more clear, you would have false positive, which is actually on the second row, negative outcome. And you also have false negative, will be on the first row, is the positive outcome. And when you add them together, these 4 cells add up to all. So that's that. So I think we cover all of them here until here. Recall, sensitivity, they are the same. By now, you would have known that these all refer to true positive rate. So why is it recall and sensitivity? If you think about it, it's intuitive, I would say. So again, the confusion matrix, this is prediction, this is outcome. So recall would be to look at the first row. Recall or sensitivity is the percent of true positive among all the positive outcomes, which true positive and false negative. So, among all the actual positive cases, let's say COVID, let's say we have 50 COVID we have 50 COVID diagnosed patients somehow, went away into the wild. We want to identify them, right? And the efficacy of our identification system is defined by recall. So let's say there are 50 among 10,000. It's a low percentage. It's hard to guess. If I give you 50 opportunities to guess, select 50 of the 10,000 people who you believe is COVID diagnosed, then, how many of them are actually selected into the 50 would define the, no, actually, there are 50. Yes, so the denominator is 50. If you are given the opportunity to select 50, how many are actually identified will become the numerator. The recall sensitivity is the capability of the algorithm to actually pick up the positive cases. So that's a recall. Of course, you can predict everybody as positive. Yeah, you can make positive prediction for all. That's one way to do that. Then you will have perfect recall. You would have perfect recall or perfect sensitivity, which means your model is sensitive enough to recognize as many positive actual cases as possible. So that's recall. But obviously, recall doesn't tell the whole story. You cannot afford to predict everything positive. Yeah. Because there will be cost. There will be cost. So the cost would be the other side of the story, specificity. Specificity is the opposite. Specificity would be a measure of how accurate the algorithm is in recognizing negative cases. So if you were to predict everybody positive, then the specificity would be 0. Because another way to say that is the algorithm is unable to recognize any of the negative cases among the, how many? 9,950 of the negative cases. So the algorithm excels in recall and sensitivity, but it failed in terms of specificity. That's not a good algorithm. So you would not want to predict everybody as positive, right? What's the cost of having low recall? The cost of having low recall is potential outbreak of the pandemic. Yeah. If the algorithm failed to identify enough number of positive COVID cases, then they are infectious. They can potentially lead to pandemic. But if you have high recall but low specificity, what's the cost? What is the consequence? If you make positive predictions, if you overpredict positive cases, then you would have to test everybody. Yeah. The moment that you predict somebody is positive, you have to confirm it. You have to take actions. Taking actions means put stress on resources. You have to test all 10,000 people, and you're probably not able to do that. You'll have to slow down all the other progress, right? So in that case, you may not be able to finish testing soon enough to be able to treat the positive cases. you know, it could be the last minute that you catch the last one. So in that case, you would quarantine the entire group. You would quarantine the 10,000 people together. The good thing is that no positive cases would have been able to be released to the wild. So you protect all the other people, except for the 10,000. But still, the 10,000 people might be, have higher risk. Or you would have to have much more resources to keep them separate at the same time. It may be very hard to do that. But that's a real problem that, health departments are faced to do. I think this has direct policy implications to the world that we live in. Think about how governments deal with COVID. In the States, as well as in most countries, I think, in Europe, UK, India, or maybe even Africa or Australia, we rarely close a city. In terms of we not letting anybody get out, close the borders. We don't do that, and it's not feasible even. It's not feasible. So if you were to close the border of a city, then that would be to take let's say, there's an outbreak in the city, and if you allow traffic flow in and out of that city, then, an outbreak is more likely to spread into neighbor cities. If you have better control, not better control, but tighter control, if you close out the city, then at least you can contain the virus in the city border. But that would require huge cost. But you can contain, you do contain the virus at least. So that would be to take a strong kind of sensitivity approach, where you basically predict everybody is potentially infectious and try to keep them locked down and try to treat them on the spot. People outside the city will be considered lucky because they have lower risk of being infected. But people inside the city will have much higher risk because they still have to interact with each other. If those carrying virus is restricted to this area, then you have better chance of getting it. It's like, on a cruise. If you're on a cruise and the cruise is not allowed to get on board, to offload the passengers, and all those that are on a cruise have a higher likelihood of getting infected. That's what happened, right? Early on last year. So, that's two different approaches. Here we don't lock down cities, and then people can travel freely on highways. That's why, we have a national level pandemic. That's kind of quite simple and can be predicted almost. So that is closely related to our life. Specificity, okay, and then, but let's see, if the model has high sensitivity and high specificity, can we say that the model is good enough? Relative to baseline models. If relative to the baseline model, the model has both higher recall and higher specificity, can we say the model is good with high confidence? Yes or no? Don't be scared.
I think yes. Would an example of a time when you want specificity to be high be like brain cancer? Because there's a high cost to, like, you can't just do a biopsy, you would have to actually cut into somebody's head, so that's pretty extreme, so you want to not.
I agree. There are certainly scenarios where you can tolerate lower recall and prefer more specificity. But I don't think brain cancer would be in that case.
You don't think so?
I think brain cancer would be an perfect example that you want to emphasize sensitivity, assuming that nobody wants to die early or lose the opportunity to treat
So what's the
cancer.
example when you would want just high specificity and you're not too worried about the sensitivity?
Justice, maybe. So you would want to have lower. I mean, yeah, I think you know, if you think about it, if you have strong law enforcement, then people have less freedom, and people are prosecuted more for the sake of high sensitivity. So basically, don't let any perpetrator go free. So in that case, you would have to prosecute more and will lead to more false positives, right? You can only have higher false positive in order to have higher false true positives, because you are making more positive predictions. So yeah, law enforcement would be, that's why I think the assumption of legal prosecutions, well, no, law,
Innocence?
yeah, assumption is innocence unless they are proven otherwise. So, and I think that has other reasons, because we don't have the resources to prosecute everybody. So, I think that's both resource-wise, but also in terms of, better tolerance. Yeah. So in terms of cancer, I would say we want to emphasize recall and loosen a little bit on specificity. But there's always it's always relative. There's no perfect point. Even for fire alarm is relatively less costly, not as severe as brain cancer, but still, lives can be lost. So, but can you tolerate too much false positive? You cannot, because too much resources. That, I think this is actually what the reality is. False positive at fire department is very high. It's very high. Is that justified? That's a question. There's always there's no perfect point. Depends on how much you want to waste in terms of resources. How much waste is tolerable, right? And it can change from time to time based on policy. Yeah. So, but to answer the question, if a model has better recall and specificity than the other models, then you can say with confidence the model is better, because there is no other sides that are missed. That too is basically all the considerations that you can have. So in terms of high recall, what does that mean? It means that in the first row, you have very high percentage of true positive, right? Of the true positive and false negative, the majority is true positive. In terms of specificity, in the second row, the majority are true negative. So not only does the model have higher accuracy, if you look at the true versus false, the model also is doing well on both the positive outcome and negative outcome. And that there really isn't any other, hidden aspects. So, so if you have high recall and specificity, the model is doing well. And that's a concept behind F1 score. F1 score is a composite measure that incorporates both of them in a complex way, not that complex, but a little bit, which is essentially to say, if F1 score is high, it's not very possible that the model will suffer either low recall or low specificity problem. But if the F1 score is low, there could be 3 different scenarios. Both the recall and specificity are low. Recall is good, but specificity is low. Or recall is not good, specificity is okay. If the model sucks in one area but not the other, you may be able to argue the model is still doing well, depending on the problem, right? So it's hard to say, but it's kind of troublesome if you always have to look at 2 numbers. If you have a measure that incorporates both, and you can have a clear judgment in some conditions, it's always better. So high F1 score would mean, that you can comfortably say the model is doing well, and even after considering both outcomes. So I'm not going to, demonstrate these. I did that last time, and you can flip the, slides yourself. And I think you get the idea. It's mostly columns and rows, and knowing the labels. You want to hold on. F1 score. And talk about that first. So, oh, sorry. So F1 score does not include that too, actually. It has a recall, yes, but the other one is precision. I think you can make an argument that you can have an alternative F1 that includes recall and specificity, but the way F1 score is defined, it focuses on the positive label, and considering true and false positives. So in terms of recall, the center of focus is this one. Maybe it makes it easier to remember. It focuses on true positives. So recall is the percentage of true positive of the first row. Precision, which is positive predictive value, which is the correct positives among all the positive predictions. So in that case, it's the first column. So still, it's a percentage of true positive among the positive predictions. So the focus is all the positives, true or false, right? So if you have both high recall and high precision, you can almost guarantee you have a good model. If you have low F1 score, maybe one of them is bad, or maybe both of them are bad. And we can look at some scenarios. If let's say we have 100 cases, and and the algorithm predicts. Let's do this first. Let's take a look at the scenario where F1 score is high. If you have recall equal 1, precision equal 1. So both of them are perfect. If you have both of them perfect, then you would have a perfect F1 score. F1 score allows the denominator to be expanded more relative to the numerator, because you see both measures are between 0 and 1, right? If you add them together versus if you multiply them, the punishment is less. So the addition is not punishing anything, I guess, non-linearly, but the numerator, if both of them are decimal, is kind of punished, one punishing the other, right? So the rate of reduction on the numerator is faster. The rate of reduction on the denominator is slower. So it tends to be smaller overall after you calculate that. Adding a factor of 2 is just to make sure if that's perfect, that should be perfect. So if all of these are 1, then you have 1 over 2, and times 2, it becomes 1 again. So 1, so it scaled back to the same region, still between 0 and 1. But if any of these are not perfect, then you would have almost certainly have a lower F1 score, but still close to 1. If it's as long as it's close to 1, it's good, right? Now we can take a look. If this is 0.9, if both of them are 0.9, what will be the score? We have 0.81 on the numerator. We have 1.8 on the denominator. And if we have a 2, then we can, kind of do the math. So it's 0.81 over 0.9. Not as close to 1 as compared to if you consider the average of these two is 0.9. Not as close to 0.9, but it's still close enough. So, the score didn't change too much from the two. So a high F1 score means a good model. But if one is low, but the other one is perfect, what will be the scenario? So here we have a scenario where we have the algorithm predicts positive for 100 cases, and we end up have 1 true positive and 99 false positive. Okay, so and we have 0 here. So there's only 1 actual positive cases. All the other are negative, but the algorithm predicts positive for all. So that's kind of similar to the previous example. In this case, you have a recall of 1. Yeah? Recall is where you calculate the percentage of this true positive of the first row. You have recall of 1. And precision, you have 1 out of 100. 0.01 is precision. 0.01, almost 0, right? Almost 0. So if you have a 1 times almost 0, it's almost 0, regardless of the denominator. So the F1 score will suck. Yeah. So in that case, F1 score can catch any badness of model performance in either of that two scenarios. So one bad performance will drag down the F1 score. That's why F1 score can quickly identify good models and bad models without having to look at 2 at the same time. So that's why we do that. So let's go through a round of exercise here, sort of case analysis, which happen to be cancer detection again, because this example is very typical. So we say the positive outcome would be cancer detection, would be cancer onset. So we're talking about malignant cancer, bad cancer, cancer that will cause further complications. But the negative outcome would be the opposite, either no cancer or benign cancer. Okay, so in this case, talking about the two errors, false positive and false negative, which one is worse to commit? Aruna? Can you say first, can you say what is false negative?
Basically, they predicted that it wasn't there, but
Hmm?
they basically, for example, they predicted that the cancer wasn't there, but it actually is.
Mm-hmm. False negative, the prediction is a negative diagnosis, no cancer, no tumor, or benign tumor, either way. But since it's false, the actual outcome is there is cancer, right? And that is worse. Why?
Because they can't treat that in a timely manner. That would be effective.
No further actions will be taken. And since the cancer actually exists, it will for sure grow and will get worse, right? So from that point on, it's going to be worse off, quite surely. Good job. So that's actually how you should think about it. If you change it, if you change the case to a business case, I hope you will apply the same, the same logic, but in there, the gains and losses will be different. In terms of customers, the gain would be revenue, or the loss could be loss of revenue. The gain would be loss of revenue, but a loss might be cost in terms of reaching the customer. Marketing costs could be like that. So, you will need to apply judgment in those cases. Any questions? The last, almost to the last. Oh, so for all the formulas, true positive rate, true negative rate, false positive rate, false negative rate, error, accuracy, as well as precision, is focusing on the positive. Both the positive, both the true positive and true both the true positive and false positive, focusing on the positive label, but could be true or false. All these concepts, all these measures, you would want to be familiar with those as if you can memorize them. But the point is not to memorize them. The point is to memorize the way the confusion matrix is, first of all, the structure of the confusion matrix, and know how, this way of layout makes it easier to derive the different measures. And once that's clear, then the measures can be derived from scratch. So the point is to memorize the way that you will derive the concepts based on solid understanding, based on no confusion, right? So that's not literally memorizing, because it's going to be hard to memorize without considering the meaning, and it doesn't make sense. It doesn't. It's not recommended. It's not like a quote that you can memorize, which has semantic meanings. These formulas don't. But the point is that the logic behind it, the concepts that are in the back. By the way, do you have a favorite quote? Do anyone have a favorite quote to share with the source, like the person? For the sake of memorizing, because if you can say the quote, then you basically memorized it. Anybody? Any quote?
I know one.
Yeah, go ahead.
It's from a movie actually, and the quote is, "There's nothing bigger than the little thing."
There's nothing bigger than the little things.
Mm-hmm.
And from which movie?
That's from Vanilla Sky.
Okay. Can you elaborate?
Yeah, just that like most people overlook some of the small enjoyable things in life, and they kind of get stressed about, or people take for granted their family. So like, you know, certain little things that should bring happiness, people kind of overlook them.
That's nice. That's life, right? It's lessons from life. Yeah. I actually looked up some. I thought I can recall something, but not really. But you know, when I look up, there are some good ones, of course. There's one from President Bush, which is, you probably can think of it. I'll let you guess which Bush. He said, "For those who achieve A's, well done. But for those C students, you can still be a president." Basically, that's great. That's rhetoric. Yeah, another one. I'll let you guess who said it. I'll try to remember. The arc of yeah, that's related. The arc of moral, I guess, judgment. See, I lost it. The arc of moral judgment is maybe long, but it always bends toward justice. Can you guess who said it? Yeah. Yeah. Great. So that's memorizing, and that's worth it, you know. But these formulas for these concepts, you don't want to memorize it, just, you know, just the way they are, but you want to understand, you know, what they mean to the sense that you can derive them by using the confusion matrix. So in a way, you're memorizing them. Okay, so the last one is here, the ROC curve. It's a little bit complex here. So in terms of using the curve, it's straightforward. So you always have this graph, and you have first you have a diagonal line, and the way that the diagonal line is going is different from the confusion matrix. So be clear on that. On the lower left side, you have 0, 0. So it's different from the confusion matrix. On the lower left side, it's 0, 1. Right? The diagonal is going this direction. But here the diagonal line is going the other direction. You always have a diagonal line. We'll say the diagonal line represents a baseline or baseline model. It doesn't mean this is an actual model. A baseline model basically means there's no model. You're randomly guessing, and you have fairly random luck. You don't have bad luck, you don't have good luck. By expectation, that's the average result of the random guessing. If you have a model that actually go like this, you can throw it away immediately, right there. You know, so that's not even as good as a random guess. So you always tend to have a model that have a concave curve, and we say if you calculate the geometric area below the line for a particular line, that would be the AUC, and C refers to curve. AUC is area under the curve. A good way to use the line, because the line is, the line is made up of points at every possible point of the x-axis that maps to the performance of the model on the y-axis. So it's made up of, hundreds of dots. You connect them, you get the line. But, how do you use that line to judge performance of the models? It's complex. Area under the curve will be the overall judgment of the model performance. And this value is between 0 and 1. A lot of the evaluation metric is between 0 and 1. Okay, so ROC curve. What does it mean? What is it graphing? What aspect of the model is it trying to describe? Let's get to know a little bit more on the axis. The y-axis typically is sensitivity. Recall. What is recall? Recall is percent of true positive out of all the positive cases, right? Think about identifying COVID cases. That's recall. The x-axis is false positive rate. It doesn't have a name. It doesn't have a different name. It doesn't have an alternative name. But let's think about it. Recall would be this one, right? That's recall. And false positive rate. False positive rate would focus on the negative outcomes. False positive. This is false positive. So false positive rate would be the percent of false positives among all the negative outcomes. And if you think about it, what is this? True negative. So if you take 1 minus the false positive rate, it's actually true negative rate. Think about it. The opposite of false positive rate is true negative rate. And what is true negative rate? If you know it, just say it. What is true negative rate? Another name for that same thing. This is sensitivity. This is sensitivity. The y-axis is sensitivity. What is the true negative rate?
Specificity.
Specificity, yeah. So the x-axis is 1 minus specificity. That's an easier way to remember. Or maybe if you prefer, this is true positive, this is false positive. Also easy to remember. But there's a reason why models tend to be in this region, and it goes like a curve like that. And if you have a model that behaves like this, never outside the boundary, of course, but my join is awful. So I'm going to just attempt. If you have a model like that, it's almost perfect, right? And why is few models behaving like that? Let's take a point over here. This model would describe a high recall, and low what? Low false positive rate, or low opposite of the specificity, which means high specificity. 1 minus specificity is low, which is, almost 0, but that means specificity is high. If the model has both high recall and high specificity, it's almost moving in one direction, keeping keeping the opposite of specificity low, and then once it's high, once the recall is high, this is actually going worse, right? In terms of specificity, because specificity is dropping, the opposite of specificity is growing. So best model would be kind of have a corner shape instead of a curve. But I guess you know the shape of that graph, but what does this line convey? Or what is the AUC? AUC 0.9, what does that mean? AUC 0.9, right? Obviously it means the area is large. It means the model can achieve high recall and high specificity at the same time. That's a good model. We talked about it. But still, what is 0.7 then? What does 0.7 mean for a model, for binary classification? So that's what I'm gonna explain here. So basically, the AUC, not AUC, the ROC curve graph can be linked to the 4 different outcomes. When you plot the regions where the points are what occupy over this line of basically from negative infinity to positive infinity, but most likely it's between 0 and 1. If you think about, this is the prediction decision, the score after activation, after signal activation for neural networks, it's between 0 and 1, right? And 0.5 is a middle point, which typically is the threshold to make a decision. If the activated value is below 0.5, you make a negative prediction. If the activated value is above 0.5, you make a positive prediction. So that's why between 0 and 5. So how are, what are these lines?
Called the classification threshold?
Yes. Or decision threshold. So let's kind of derive these points based on this. First of all, red line. Anyway, red lines going this direction will mean positive outcome. There are darker areas and lighter areas. But red always means it's positive outcome, ground truth. And blue means negative outcome. This line is the decision threshold or prediction threshold. So everything that lies to the right of that line will be predicted positive. So the prediction will be positive if to the right of the line. To the left of the line, all the predictions will be negative. So for these areas, these are the true positives. For the dark green areas, they are true negatives. And what is this? The light blue to the right of the threshold, what are these? False, which false positive, because it lies in the positive prediction region, right? And light red would be false negative. So this point here would be, so different lines, different points on this line is like to artificially adjust the decision thresholds and to calculate the performance of the model and plot the line. That's how this graph is basically made. Because when you have a model, the model has a set value of recall and specificity, right? How can you have variations? How can you have a line that varies in those areas. It's not possible. But that's actually describing a single model. So how is this line made? It's made by artificially moving the decision threshold from the maximum to the minimum, and then plot the behavior of the model under different scenarios. So let's take this point. This point would be as if the decision threshold is on the rightmost point. If that's the case, then you will predict everything to the right as positive and everything to the left as negative, which means there is no recall because there is no positive predictions. If there's no positive predictions, there is no true positives. Then the sensitivity will be 0, right? That's why we have sensitivity 0. But if we predict everything negative, we would have achieved perfect specificity. Yeah. Perfect specificity is 1, and 1 minus 1 is 0. False positive is 0 as well. So that's why this point is always lined up with 0 and 0. If we look at the other extreme, that would represent a prediction model that with the threshold that's to the leftmost point. In that case, it's the opposite. We have perfect recall, and we have 0 specificity. 1 minus 0 specificity is also 1, so that's why we have 1 and 1. So that connects the 2 dots. So in connecting the 2 dots, if a model is randomly guessing, then the line is is straight between them. But if the model achieves any better than random guessing, it will edge toward the better side of that region. That's why it tends to expand to that area. Because compared to if you compare 2 models, which is random guessing versus the other model have the same recall, but it has lower false positive, which means it has higher specificity. So this model is better than random guess. That's why. Okay, so that's how the graph is made and how that maps to 4 different outcomes. But essentially, what is the area under the curve? What does point A mean? We can actually interpret it, by borrowing these interpretations from internet, basically. And this is, in terms of interpretation, that's actually the way you want to go. Instead of, saying everything I said just now, they are very technical. You don't have to explain that to somebody who doesn't know, but doesn't have to know. This is what you want to offer as an explanation of AUC, or if you're being interviewed, you don't want to go into too much depth in technicality, but we want to talk about these. So what is the RO, or what is the AUC number? What does it mean? 0.75, what does it mean? It means, well, that 0.5 is the baseline. Anything below 0.5 is bad. It's worse than random guess. So anything between 0.5 and 1, the higher the better, or legitimate models at least. So let's say 0.75. What does that mean? It means, let me move this. It means the chance, which is 75%, the chance that a positive case, which is a positive outcome, COVID, let's say, the probability, given your model, it describes the probability that a positive actual outcome will be assigned a higher predicted score, higher prediction score, which is the activated value of neural networks. We're not talking about the label, but the label is decided by the score, right? If let's say if our threshold is 0.5, then the activated value from sigmoid function is 0.7. Then you would predict the positive prediction. And 0.7 is the score that we're talking about here. If a positive case, actual positive case, will actually have a higher assigned score than a actual negative case. That's the likelihood of that happening. What does that mean? If we do this, so we have a data set, we have outcome, we have two columns, we have outcome, 1, 1, 1. If we rank them as, you know, descending order, we have predictions, but before prediction, we have predicted score, which is the activated value. AUC of 0.75 means 3 out of 4 times you would observe something like this. The actual one case is assigned a predicted score of 0.6, but an actual 0 case is predicted a lower score. So that is right. That's, in both cases, that's true predictions. It's true positive and true negative, right? But the AUC does not take into account whether or not this is 0.6 or 0.4. So in the case of 0.4, it's actually a false prediction. It's going to predict false negative. But as long as it's bigger than 0.3, it's counted as success in the case of AUC. So in case of AUC, this would be falling into the 3 out of 4 probability, right? So that's why this is the, heavily criticized aspect of AUC. If you get something wrong with the activation value, you can still have high AUC, but your prediction outcomes may suffer. That's one limitation of AUC, if you have to say it. So if if somebody asks you what is the shortcoming of AUC, if you can explain that, maybe the other person don't even understand it, but you would hope for that they understand it. If you can say that, then you truly understand what AUC is, both the strength. Why do we use it? Because it's easy to compare models to spot good models, and typically models that have high AUC tend to be good and not having these peculiar situations, but it could be happening in theory. So that's a shortcoming of that model. Hopefully it makes sense. I'm not going to test it, so don't worry. If you want to truly understand it, go back to the video and replay and try to understand it. This is the core of data science, I would say. So try to understand it if you want to really, be good at data science. If not, you would rarely face a problem like this in real practice. I guess, I mean, in areas not dealing with data science. Okay. So, so to conclude, we have all these measures. We have accuracy, error, true positive, true negative, false positive, false negative, precision, recall, a lot. The point is, you don't have to look at all of them. I mean, even you can derive some from the others, right? Some of these are logically opposite to each other, but you don't have to look at everything at once when you judge a model. But the basic rule of thumb is you cannot only use one. That's not acceptable. If you only look at recall, it has high recall, you say this model is good, that is making a mistake because you overlook other possible scenarios. And those scenarios are really possible, right? you can have high recall but low specificity. That can be a bad model. So never only look at one, but you don't have to look at all, but at least you look at several. And there are some agreement on what the several are. You typically you start with a overall performance measure, which is accuracy. Accuracy doesn't discriminate between positive and negative, right? So if the data set is imbalanced, have a lot of negative but few positive cases, you can have high accuracy by predicting everything negative, and that model has high accuracy. So that's why it's not enough to only look at accuracy, but you have to go into the positive and negative region to look at recall, maybe specificity, depending on whether which one is more important to the business problem. And you also want to look at F1 score, because by looking at F1 score, you would have looked at both, recall and precision at the same time. And lastly, people almost always look at AUC. So that's why when I showed you the table, these are the four measures that I adopt: accuracy, AUC, F1, and recall. And if you look at other papers, you may not have accuracy, because after looking at these, it's almost not really necessary to look at AUC. Some will look at specificity instead of accuracy, but looking at 4 would be typically enough. You don't have to look at 6 or 7, but looking at 1 is definitely no. 2 will kind of indicate that you're a newbie, but look at 3 or more than 3 is a good practice. Any questions? That's it. For the hands-on, the videos will be very clear and helpful, I hope. And so, if you have specific questions about the coding, I'll be here after class. We can solve that. Otherwise, we can go home.